Hello, we are presenting our recent paper, Gender Slopes, Counterfactual Fairness for Computer Vision Models by Attribute Manipulation. My name is Jung-Suk. I am an assistant professor in communication at UCLA, and this is joint work with Kimo. The central question we want to ask in this paper is, how should we measure fairness of any AI or machine learning systems? And this is not a trivial question because there are a number of different measures or metrics one can use when evaluating the fairness of a model. And this is not a unique problem in the machine learning literature. For example, equality outcome versus opportunity has long been debated in our society in general. And there's no single method to satisfy all of these conditions simultaneously because they are concerned with different objectives which may conflict with each other. So in this paper, we focus on a recently proposed framework of counterfactual fairness as a novel way to identify hidden biases and measure fairness of computer vision models. As its name suggests, the counterfactual bias is based on causal inference, unlike other methods based on statistical analysis on observations. In the past, researchers mainly used observational analysis to audit a classifier and black box models. And one of the most famous examples is gender shade, recently showing the accuracy disparity of computer vision APIs. They tested whether commercial classifiers can accurately classify the gender of a given face equally well on different gender and races. And their main finding was all the classifiers that they tested were performing less accurately on images of female or dark-skinned. And note that these conditional probabilities can be only measured on different non-overlapping subset of data, meaning different individuals, because one cannot be both black and white or male and female at the same time. This approach cannot rule out the possibility of alternative explanations. So even if there exists a disparity between two probabilities, we're not able to draw a conclusion of what exactly is driving the disparity. It could be race or gender, but it could be also due to other non-sensitive attributes such as image background. In contrast, counterfactual analysis can help us identify exactly which features or variables are driving the biased model outputs. And this can be done by making an intervention on the same individuals. A classifier is counterfactually fair if its output remains the same if the same person had different gender. So in other words, we want to enforce each person to have different gender than their own original gender. And that is not possible in the real world, but luckily in computer vision, we can use recent generative model to manipulate the image content. In computer vision, a recent paper written by Denton et al. Showed that it is possible to use GAN to manipulate face attributes and measure the classification sensitivity using the generative counterfactual examples. And then the main question that they ask is whether changes in one attribute will cause changes in other attributes. There are two limitations in their approach. First, they did not separate the sensitive attributes from other attributes in training, which means the counterfactual examples may contain the internal correlation between those variables. And in addition, their method was only tested on public dataset, which is CELOP A. And in this dataset, we already know the correlations between attributes from the label. In this paper, we propose a novel framework to generate counterfactual examples so that we can only change the sensitive attributes such as race or gender while keeping the other variables intact. Our method is mainly based on fader network, which is a recently proposed method for image attribute manipulation. But in this paper, we added another layer of constraint to make sure the model keeps the same level of smile and age in generating outputs. And this was necessary because the data sets we used to train this model often contain biases and spurious correlations, such as in setup A. So once we trained the model and obtained the counterfactual examples, we used these examples to measure counterfactual fairness for black box computer vision APIs. These APIs are provided by many different companies and widely used for practical applications. And these APIs are useful for many people because those are already pre-trained with huge number of labels and also great amount of images. And because these APIs have been used as a part of real-world systems, their result and any internal biases will likely have large real-world impact, which we want to analyze in this paper. These classifiers can detect many different labels from images, but we focus our analysis on profession-related concepts in this paper. Profession-related concepts such as a doctor or nurse or engineers are very important to understand because we already know there's a huge gap between gender or racial participation in these groups of occupations, which further lead to income inequality in the society. And we want to test whether the classifier would produce identical scores on those profession-related concepts, whether it's an image of male or female counterfactually generated. And for this study, we constructed a new data set of images showing people in various occupations. And we used the list of the most common job titles in the United States published from the Bureau of Labor Statistics. And this is the overall process in the pipeline at inference time. For our given input image, we first detect and align a face. And we crop this facial region and then send to our model to generate a series of facial images which have been modified on the dimension of gender or race. And then these modified facial images will be then sent back to the original image background. And this series of larger original images will be then sent to the APIs, from which we obtain a sequence of scores on the concepts about professions. And these are some of the examples of the modified facial images, which have been modified for the gender. And these are the actual output that we obtained from the API by using the sequence of modified images. And for each cell, you'll see 3 images. And the center one is original images without any modification. And then images on the left side are the images with increased femininity. And then images on the right side are the ones with increased masculinity. And as you can see, this classifier showed a tendency to assign higher confidence scores for the concept of doctor or surgeon to male version of images, and also assign higher scores for the concept of nurse to the female version of identical images. A similar pattern could be found for the concept of engineers, scientists, or researchers. And in this case, these classifiers tend to assign higher score for the male versions of identical images. And these are the results obtained from the entire data set. you can see a similar pattern where this classifier tend to assign higher score for the concept of nurse to the female version of images compared to the male version of the images. This is the list of concepts for which the classifier tend to assign higher scores for male images. And this is the same list for female. And these concepts are all statistically significant. Another important question that we should ask is what could potentially cause the biases in these classifiers? And one probable answer to that question is the biases in the dataset originally used to train those models. To validate the potential link between media bias and AI bias, we also measure the gender representations using the same occupational images that we collected from Google Image Search. And not very surprisingly, we were able to identify fairly strong unbalanced gender representations for the most of the concepts that we analyzed. In summary, we proposed a novel framework to generate counterfactual examples by using generative computer vision models, which can be used to measure counterfactual fairness for black box computer vision models. Fairness is an important direction for ethical AI and multimedia research, which is relatively oversight in the community in the past. But it'll be increasingly more critical as more AI systems will be deployed in society, and we'll need collective effort to address these concerns effectively. Thank you.